Greetings, and thank you for attending this presentation of ITSC. My name is Zhou Qiaozhao, and I'll be presenting today for our development of a data-driven modularized model of a plug-in hybrid electric bus, or PHEB, for connected and automated vehicle applications. In a collaborative effort with Oak Ridge National Laboratory and US Hybrid, as part of the Department of Energy's APARE Next Car program, UC Riverside developed a plug-in hybrid electric transit bus, collected the data using a novel data-in-the-loop methodology, and developed a modularized PHEB model through this data. In this presentation, I'll focus on the PHEB modeling part of this project. I'll first describe the motivation and then introduce our testbed for collecting data. Next, I'll explain the system architecture and modeling methodology. And finally, I'll present the evaluation of the model, including both the standalone performance and the cascaded performance. Transportation energy consumption and environmental impacts have been a long-term concern for decades. To address this issue, a wide range of emerging technologies and research have been developed from different perspectives in the area of intelligent transportation system, or ITS. Among them, connectivity and automation and electrification are the two topics that are mainly discussed. In the connectivity and automation perspective, the problem can be addressed in three different scopes. Traffic management strategies, like RAM control systems, can reduce congestion and speed fluctuations at the macroscopic level. Vehicle dynamic optimization strategies, like cooperative adaptive cruise control and eco approach and departure, can also be used to plan more efficient trajectories for vehicles to follow. And the powertrain optimization strategies, like intelligent energy management, can improve the energy utilization ratio. In the electrification perspective, especially in the hybrid electric vehicle context, the reduction of energy consumption and pollutant discharge relies on the following reasons. First, when the vehicle is powered by both an electric motor and an internal combustion engine, a smaller engine can be used. Second, electric motor and engine can be designed to operate only in their most efficient regions. Third, regenerative braking can recapture a significant amount of energy that would have otherwise been wasted. Understanding the vehicle dynamics, including not only the speed response, but also the detailed operating status, can assist researchers to design, test, and validate the aforementioned system and strategies. And it is essential to have an accurate, complete, and flexible vehicle model. A transit bus is a good target for introducing the new ITS techniques, since it plays an important role in the city's public transportation system. Specifically, it is proved that a PHEB can achieve a 28 to 48% fuel economy improvement. The challenges for building up an accurate, complete, and flexible model for PHEB are as follows. First, this type of heavy-duty vehicle usually has a low power-to-mass ratio and large actuator delays. Also, the combination of both internal combustion engine and electric motors makes the vehicle dynamics even more complicated. Further, the different powertrain configurations with different mechanical properties also complicate the modeling process. For example, the vehicle control unit level power and battery management logic are often unknown to the researchers. As a result, the physics-based modeling approaches or the end-to-end learning-based approaches does not accurately capture the detailed features of individual components or processes, such as regenerative braking, engine drive, torque converters, and transmission. Therefore, we proposed a modularized PHEB model, which based on the physical structure, and for each module, the neural network has been adopted, which can provide accurate prediction of detailed system states. The PHEB modeled in this research is a CNG transit bus that has been hybridized. As shown in the right-hand figure, the 51-inch frame extension accommodates the electric motor in the driveline. The bus was tested on the Mustang heavy-duty chassis dynamometer, and we used our dyno-in-the-loop platform to collect the data for modeling. This slide shows the hardware components equipped on the PHEB for the dyno-in-the-loop platform. Specifically, we'll need a forward range radar, DSRC for vehicle-to-infrastructure, a driver's aid for speed recommendation, and a data acquisition system. Our modularized model is based on the physical structure of the PHEB, which will be introduced in this slide. The vehicle uses a power split hybrid approach, where the internal combustion engine and the electric motors are coupled so that they are able to power the vehicle either individually or together. The power split logic is programmed into the onboard computer, or VCU, to select proper torque output with a different proportion from both ICE and EM. In addition, through such a hybrid system, battery management strategies like regenerative braking have been adopted. The dashed boxes in this figure illustrate the key components of the PHEB that are modeled. The human driver model considers the interaction between the driver and the driver-vehicle interface. Based on the suggested speed and current vehicle actual speed, the driver responds by pushing the acceleration pedal or the brake pedal. Then, based on the current vehicle status and the position of two pedals, VCU calculates the power split logic and sends it back to ICE and EM. A clutch is used to govern the transition between different modes, like ICE only, electric only, and hybrid. Because of physical constraints and some low-level controller logic, the actual response varies from the torque command. Therefore, the ICE module and the EM module depict the torque response based on the torque command at the vehicle status. Next, battery dynamics can be updated according to the usage or charging mood of the EM. Afterwards, the transmission module reconstructs the automatic transmission shift schedule. With all the above vehicle status predicted, the powertrain dynamic module mimics the key status including vehicle actual speed, ICE speed, and EM speed. Finally, the predicted actual speed is sent back to the human driver module for the next iteration. The detailed input-output for each module are shown in this table. It should be noted that although there are two separate electric motors, both of them are linked together and respond to the command in the same manner. Therefore, they are modeled as a whole. When connecting all the modules together, the cascaded vehicle model takes the reference speed, initial SOC, and other initial vehicle states, like initial vehicle speed, as the input for the overall system, marked in blue in this table. This slide introduces the modeling methodology. We treat the dynamics of the PHEB as a discrete system with 1 Hz update frequency. The LSTM neural network is chosen to be the training algorithm because of its significant ability of fitting complex dynamics with a large amount of sequential data. At each time step, the modules can predict the values of corresponding output for the next second based on the input from the current time step, hidden and sealed states from the previous step, and the initial states. The neural network consists of LSTM layers, fully connected layers, drop-off layers, and nonlinear activation layers. The dropout layer is adopted with dropout ratio of 0.2 after each LSTM layer to prevent overfitting. Rectified linear unit is chosen to be the nonlinear activation layer for the network. The detailed structure shows in the bottom table. Because the transmission gear level only has 6 possible values, a classification layer is used as the last layer instead of a regression layer. Here we first evaluate the stand-alone performance of each module. The mean absolute error, or MAE, and the normalized MAE are calculated for all modules, except the transmission, where the accuracy of the transmission gear ratio was used as the performance index. The NMAE normalizes the error to be between 0 and 1. As can be seen from the table, all the NMAE values are smaller than 0.1, and the prediction accuracy of the transmission selected gear ratio reaches over 90%, indicating the excellent performance of all modules in the system. To evaluate the cascaded vehicle model performance, a random trajectory is selected as the suggested speed profile for both the driver and the proposed model. Then, using the dynamometer-in-the-loop platform, the driver tries to follow the speed profile as accurate as possible. The criteria for the driver in this test are the same as the one when collecting the training dataset, which is to follow the provided speed profile as close as possible. The speed response and other aforementioned data are collected to be the ground truth. The cascaded vehicle model is built at the Simulink platform. Each module corresponds to a block in Simulink, and the blocks are connected based on their input-output relations. Only the suggested speed profile and the necessary initial state are required for the Simulink. The simulation results are shown in the next 2 slides, where the red curve shows the predicted value from the proposed model, and the blue curves shows the ground truth from the dynamometer-in-the-loop platform. In general, the cascaded vehicle model successfully predicts the signal with the correct trends and acceptable approximate value. We can see the negative torque provided by the EM presents a good example of regenerative braking. The ICE output converting from low value to a higher one depicts the idle speed control and torque converter precisely. However, we can also see the error gathering from the upstream to downstream. One example is the inaccurate prediction of the human driver module during the very first 20 seconds. As a result, upshift-downshift maneuver is predicted inaccurately by the transmission module, and the powertrain dynamic module miscalculates the zero speed. To sum up, we proposed a data-driven modularized model for PHEB using the deep learning approach with LSTM networks. We designed the modular structure according to the physical architecture of the vehicle platform, and LSTM networks based on the property of each module. The performance validation of the standalone modules shows great accuracy in modeling the vehicle subsystems. The cascaded vehicle model is able to predict numerous signals and depict the vehicle dynamics with the correct trend and approximate value. The results show that given the initial states without update any ground truth information, the error of the model does not grow along time. Moreover, the availability of key signals such as SOC, engine fail rate, and transmission shift schedule provide potent support for testing use or controller design. This research is supported by the U.S. Department of Energy under the ARPA-E NECTAR program. We would also like to thank to the colleagues from UC Riverside, Oak Ridge National Laboratory, and US Hybrid for their strong support and constructive comments for the platform setup. That's it for the presentation. If you have any questions or comments, please feel free to contact us.